We can talk about motion in two dimensions by building on what we've learned about one-dimensional motion. In a one-dimensional world, life would be simple. Imagine, if you wanted to go meet someone to study physics together, all you'd need to know is how far to go.
Excuse me, can you tell me which way Dr. Smith's office is?
Yes, 2 doors down.
Thank you.
In two dimensions, knowing how far to go is not enough. You also need to know which direction to take.
Excuse me.
Yeah.
Can you tell me which way Dr. Smith's office is?
2 doors down.
But which way?
Oh yeah, that way.
Thanks.
To describe motion in two dimensions, we use vectors. For example, the boat on the water is moving in one dimension, but the parasailer pulled by the boat is moving in two dimensions. Thus, to describe the motion of the sailor, we need vectors. In two-dimensional problems, the motion can be broken down into the x and y components, where x is usually taken to be along the horizontal direction and y along the vertical direction. Displacement in two dimensions is described by the vector delta r, which has components delta x and delta y. Displacement in two dimensions can be considered as being the vector addition of the displacement components in the x and y directions. The magnitude of the displacement vector, or of any vector for that matter, is its scalar length, which is the square root of the square of the two components added together. A vector can also be written using components. If the angle between the displacement vector and the x-axis is theta, the x and y components can be written in terms of sines or cosines of theta, multiplied by the total displacement. For the displacement vector triangle, what is the tangent of theta? Choose the answer you think is correct. Correct. Yes. From basic geometry, we know the tangent of theta is the length of the side of the triangle opposite the angle theta, divided by the length of the adjacent side. In other words, the tangent of theta is delta y divided by delta x. Like displacement, velocity and acceleration in two dimensions can be written as vectors and can be broken down into x and y components. Keep in mind that motion in two dimensions involves vectors, which are determined by two quantities, magnitude and direction. Do you remember the kinematics equations of motion in one dimension for constant acceleration? Choose from the list to proceed. Correct. How do the one-dimensional kinematics equations for constant acceleration differ from the two-dimensional equations? To describe two-dimensional motion, we need vectors rather than just scalars, and thus more information must be specified. As a result, there are more equations to deal with. A classic example of motion in two dimensions is projectile motion. In this case, the arc, described by the basketball after it leaves the shooter's hands, is that of a projectile. Let us assume that the projectile, in this case the basketball, is launched with an initial velocity, v0, at an angle theta with respect to the ground, which we assume to be in the x direction. We can use the two-dimensional kinematics equations of motion to figure out things like how far and how high the ball goes. Let's begin by writing down what we know, starting with gravity, which is constant. With x in the horizontal direction and y pointing in the vertical up-down direction, which set of equation describes the acceleration? That's correct. There is no acceleration due to gravity in the x direction, only the y direction. Now, what do we know about the initial velocity? We are given the magnitude, v0, and the direction, angle theta, with respect to the x-axis. Use this information to figure out the components of the initial velocity. That's correct. Equations describing motion in the horizontal direction usually involve cosine, and those for the vertical direction usually have sine. Now, using what we know about the acceleration and initial velocity, we can write the equations of motion. If we assume the ball is launched from the origin, we can take the initial positions, x0 and y0, to be 0. This considerably simplifies the equation. In our consideration of the equations for x and y, Let's first solve for time using the x equation. Next, we substitute the equation for time into the y equation. Notice that the y equation depends on x and x squared, which, I'm sure you recall, is the equation for a parabola. This means that the trajectory of the basketball, or any projectile, follows a parabolic curve. The equations of motion for a projectile can be used to reveal other interesting things. These include how far in the horizontal direction the projectile moves for a particular initial velocity and angle, which is called the range, and is labeled r, and how high up the object goes, or the height of the trajectory, which is usually called h. First, notice that when we use the standard convention of x representing the horizontal dimension and y the vertical, the object starts its motion at y0 equals 0, and when it returns to Earth again, y final also equals 0. If we set x equal to r for this situation, we can put this into the equation we previously derived for y, in which we eliminated the time parameter t. Now solve for r. Notice that r can be canceled from each side of the equation, and writing tangent equals the sine over the cosine gives an expression for the range.